Hi, let's review about life of star. And this is everything that you need to remember for your upcoming IB test. Okay, on star from a nebula. What is a nebula? It just means a cloud of gas and dust, and stellar means that related to star. So stellar nebula is the beginning of all stars. And then it becomes a protostar. Protostar is not a star yet. It's just like pro here before a star. Okay. Then you have on star begin as main sequence star, and each star will have its own mass to begin with. So if you have pretty like low mass compared to the sun, it up to like 1 or like 2 mass of the sun is classified as low mass star. Okay. When it goes from 2 to 8 times the mass of the sun, it is an intermediate star. Okay, and if the mass is greater than 8, it is a high mass star, and high mass star will have a blue color. That's why you can see the blue colors here. The other star will look kind of like yellow or white. Okay, then this is the life of a low mass star. You can see that after a while, when it burns on the fuels, it will have its radius become larger, like just before an explosion, it become larger. And it's just look really red. It's hot and red. And the radius is greater than 10 times the radius of the sun, or even more, up to 100. If it's a more than 100, it will be a supergiant. And supergiant also red. So that's why we have red supergiant star. Okay. Now let's just come back here. This life cycle of low mass star, it will become a red giant, and then after that, it just become a nebula again. Okay, but this is the nebula of the dying star. So that's why we have the name planetary nebula to distinguish with the stellar nebula, which doesn't have nothing to do. It doesn't have nothing to do with the planets. It's just named like this to remind it that is the dying star. Okay, after the dying of the star, and after that, what is the end? It's become a white dwarf. Okay, so white dwarf here also follow a limit that is discovered by Chandrasekhar. Okay, that's why we have his name here. Like the Chandrasekhar limit will say what? It says that on the white dwarf star should have the mass just less than 1.4 the mass of the sun. So what if we got some star that greater than this one? It will be another story here, then we can talk about it later. So the white dwarf star here, if it has some nearby star, then it can accrete the mass from that star, and it can lead to a nova or supernova. Okay, so supernova and nova basically just like an explosion. Now, if we start with a high mass star, and there's two a possible fate for a high mass star. If it like up to 25 times the mass of the sun to begin with, you can see that after the burning, in the end it can have the mass just less than 2 times mass of the sun. So in this case, it will become a supergiant, and also like come through a supernova, basically means explosion, and then it will become a neutron star, which is really heavy, with a very high density. And it also follow another limit, which is called the Oppenheimer-Volkoff limit, which is nearly figured out to be like 2.17 mass of the sun. So basically, if you got like in the end, if that star is just around less than 2 mass of the sun, or like 2.17 mass of the sun, then it will become a neutron star. Okay, so in the last case, when the beginning star here is really huge, really heavy, like 20 to 100 times the mass of the sun, it also goes through a supergiant and then supernova, and then it becomes a black hole. Okay, so in the end, the mass of the black hole can be greater than 2 mass of the sun, or even larger. Okay, so we have to remember that star begin with a different mass, which is called the progenitor mass, and then in the end, it will be end with a pregnant mass. Sounds good? Okay. That's about the life cycle of the star. And sometimes you can see that they ask us to do calculation, and also like we need to identify what kind is the star from the HR diagram. So basically, this is the only equation that we need to remember, and this equation can be found from the theme B in the data booklet. Okay, so here L is the luminosity, basically like the brightness of the star, how much brightness, how bright is the star we can see from the sky, and usually it is compared to the luminosity of the sun. We have the luminosity of the sun as a unit as 1, and then we compare the brightness of the star to that of the sun. And then it will equals to, this is the Stephen Boltzmann constant. You can also find this constant from the data booklet. And A here is the surface area, and this is the area of a sphere. So it will be 4 pi times with the radius square. And the luminosity also depends on the temperature of the star up to the 4th power. Okay, remember that. So whenever they ask you to do calculation, you can just use this equation. Another thing to remember is that the luminosity of a star depends on the mass, okay? And you can see that actually different with different kind of star with different mass, the power is different, but on average it's around 3.5. So sometimes they can give you problems to compare like the radius of the star, the temperature of the star, and also the mass of the star compared to that of the sun. Then you can just see that from here, we can see that the ratio, this is a constant, so it can be cancelled out, right? Then we just have this one, the ratio of the radius square, and the ratio of the temperature to the 4th, okay? So try to make use of this one to extract the information about the star, like the radius of the star and about the temperature of the star. So then if you got to know, okay, how hot the star is, we can identify it based on the HR diagram. So basically on the HR diagram, they will just divide them into 4 regions. The first region, and we have to identify the sun, okay? We need to see the sun first. So the temperature of the sun is like 5,700 something Kelvin, okay? So it's around this position. You can see that in here we have like 4 regions. A supergiant somewhere here, okay? Another giant region here. You know, supergiant is like the red, is on red color. Oh, I should have them color in red. Then you can remember better next time. This is supergiant in red, also giant here in red. And then we can see that the star, our yellow star here, the sun here, okay? At the luminosity 1, and at the temperature around nearly 6,000, I could say, because it's like 5,700 something. And then we have the white dwarf somewhere here, okay? So you can see that the region for the white dwarf is just luminosity below the sun, okay? It's not bright at all. And also the temperature. A thing to remember about the HR diagram is that when you're going from right to left, that's the increase direction of the temperature. You see, this is really hot, and this is like cooler, okay? This is hotter, okay? That's the key thing to remember. So you can see that this is the white dwarf region, and then here, this is the giant. So how can we distinguish between the giant and the supergiant based on the luminosity, okay? 1,000, okay? If it's a star brighter than the sun but less than 1,000 times, okay, this is the ratio compared to the luminosity, that would be giant. But if it's above 1,000, that should be supergiant. Easy, right? And you can also see that the temperature of the supergiant and the giant is less compared to the sun. Okay, so white dwarf less, the luminosity is less and also harder. Okay, And for supergiant and giant is like cooler and it's brighter. Sounds good? Okay, so that's everything for stars. I hope that you will nail all the questions related to star in your exam. Okay, good luck. Thank you.